When you speak into a phone, your voice doesn't travel through the air to the listener. It is instantly translated into a physical surge of electricity. For decades, early communication networks transmitted this electricity in an analog format. The voltage moving through these copper lines was designed to mirror nature, continuously rising and falling to match the exact shape of your voice. But every wire, radio wave, and fiber optic cable passes through the physical world. Lightning, heat, and even the hum of neighboring cables constantly bombard the line, adding random electrical interference known as noise. This chart shows exactly what happens to an analog signal in the real world. The smooth, uniform sine wave is disrupted by jagged spikes of electrical noise. Because the original wave is continuous, the receiver cannot know which bumps are the actual message and which are just static, and it gets worse over long distances. As the signal fades, engineers use amplifiers to make it louder. But when you boost an analog signal, you boost the noise right along with it. The farther an analog signal travels, the more distorted it becomes. Since you can never perfectly strip away the environmental noise, building a flawless global communication network on continuous waves is physically impossible. In 1948, an engineer named Claude Shannon published a paper proposing a radical alternative. Engineers needed to stop trying to mimic nature. Instead of sending a continuous fluid wave, Shannon proved that any message could be chopped up into distinct, discrete values, zeros and ones. But this introduced a paradox. Computers do not possess a magical way to transmit numbers through the air. To get a bit from one place to another, you still have to send electricity over a wire. You still have to use analog physics. This chart shows how distinct values are built. Digital signaling uses analog electricity by assigning rigid rules. A positive voltage pulse lasting a specific fraction of a second equals a 1. A negative pulse, or total lack of voltage, equals a 0. By forcing continuous electricity to represent strict mathematical states, engineers finally decoupled the integrity of the message from the vulnerability of the physical wire. When a digital pulse travels down a noisy channel, it still gets battered by electrical interference. By the time it arrives at the destination, it looks just as jagged and distorted as an analog wave. But the receiver's job is completely different now. Instead of trying to perfectly trace the wave, it only makes a binary guess. If the incoming voltage lands above a set horizontal threshold, the receiver records a perfect 1. While extreme noise surges can occasionally flip a bit, the threshold filters out the vast majority of interference. Engineers map these rare failures as a probability of error. Because the receiver confidently regenerates a pristine 1 or 0 from a degraded pulse, digital information never wears out. It can be copied and relayed infinitely without losing a single drop of detail. This indestructible data allowed us to abandon the rigid infrastructure of the telephone era. Making a call used to require a continuous, dedicated physical copper wire connecting you to the other person for the entire duration of your conversation. Because digital messages do not degrade, they no longer require a dedicated circuit. A file can be chopped into pieces, shared over time, and sent completely out of order. This strategy is called packet switching. A single message is broken into small, uniform packets, and each one is individually stamped with a sequence number and a destination address. The modern network acts exactly like a postal system. Specialized computers, called routers, act as mailrooms. They read the address on every passing packet and independently forward it down the most efficient available path. By treating data like mail, the network can use dynamic routing. If it detects congestion or a failure on a central link, it automatically detours the remaining packets through alternate pathways to keep the data moving. Our modern devices still rely entirely on the chaotic, fading physics of analog electricity. But by layering strict digital mathematics and self-correcting packet protocols over that electricity, we bypass the limits of the physical wire, building a communications network that can scale endlessly without